Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to differential calculus students or students enrolled in Calculus 1 who are just beginning to learn about limits. Now, limits, this is a huge topic in calculus, and so we should take our time kind of stepping into it very slowly so you really get a good understanding of what a limit truly is. And the way we're going to do this is we're going to start with the idea of what a secant line is and what an average rate of change is, at least for this video. So let's start with a secant line. In a very basic form, a secant line for a curve is a line that intersects the curve more than once. Now what you see right here is a function f that I just drew down very quickly. And we're saying that a secant line to that curve is any line that intersects it, again, more than once. But that's actually a pretty vague definition, mainly because we need to really talk about where it intersects the curve. For example, this technically is a secant line, but it's not a well-defined secant line. It could be considered a secant line that connects this point right here to this point right there on the curve. And that's because there's an ambiguity here. In other words, that it could have connected those 2 points, or it could connect this point to this point. Because we have those ambiguities, this is not a well-defined secant line. We need to really talk about how to define a secant line properly. Suppose that we have this point, a comma f of a. This exists on our curve f. And let's say later on we have another point. The other point, let's call that b comma f of b. So it's at x equals b, y is equal to f at b. Now that we have those 2 points labeled, we can really talk about the secant line going through those points. It's just a line connecting those 2 points. And so we just line this up, pun intended, and we go ahead and draw our line through that. That would be the secant line going through the points a comma f of a and b comma f of b. Now, as you can see, this definition then that we wrote up above, it's a pretty vague and probably not the best definition that we could have. To be honest with you, when you talk about a secant line, you're saying a secant line that's going through 2 very specific points. And so you want to tell the world what those 2 points are. As a heads up, what we're going to end up doing is drawing one of those points closer and closer to the other. For example, a, and I use a comma f of a because I consider a to stand for anchor. So a is our anchor point. What we're going to do is with the non-anchor point, we're going to allow that non-anchor point to get closer and closer and closer to x equals a, the x value of that point, that is. And so as you see, let's just pretend that we drag that point b comma f of b over to this point right here. When you do that, your secant line is different, right? It technically now has a negative slope to it even. Whereas the original secant line going through b comma f of b and a comma f of a had a positive slope, this one now has a negative slope. But those 2 points, a comma f of a and b comma f of b, are getting closer to one another. And that's exactly what you want to work with when you work with secant lines. You want to force those 2 points to get close to one another. Now I'm sort of getting ahead of myself, so let's go ahead and step forward to the next page and look at an example. Graph the function and the secant line to the function going through the points 2 pi over 3 comma f of 2 pi over 3 and pi comma f of pi, and then find the equation of the secant line. And our function in this case is f of x is equal to 2 cosecant of 1/2 x minus pi over 6 and quantity plus 1. This engages a lot of our prerequisite skills, specifically our graphing skills from trigonometry and pre-calculus. So let's go ahead and review that topic very quickly. The first thing you should realize is that when you are about to graph any type of trigonometric function that involves shifts, like this has a horizontal shift, you really should factor off the lead coefficient of x here off of both of the terms in the argument of your trigonometric function. So let's go ahead and just simplify this statement and say that f of x is equal to 2 times the cosecant of, and I'll factor off a half from x and from pi over 6. I'm left with a pi over 3 there. You can double check my work. If you distribute that pi 1/2 across to each of these two terms, you will get 1/2 x minus pi over 6. So that is perfectly fine. And then plus 1. The reason why I do this is it just tells me every little piece of information I need to graph my base function, which is the sine. So the first thing I'm going to mention, and I'll write this in blue off to the side, is that the amplitude of our sine function that we're about to graph is going to equal 2. Remember, that's what this stands for, is the amplitude. Technically, it's the absolute value of that. If you need a review of that, I have a whole review series on graphing trigonometric functions. It is going to be somewhat important, not actually a ton, but it is somewhat important in calculus. The next thing you're going to worry about, I read these from left to right, if I called that a and this coefficient of x b and this constant here c and this constant here d, the next thing I'm going to worry about is what effect b has on the overall picture of the sine that I'm going to graph, and therefore the cosecant. 2 pi over b is going to be the period. So the period of what we're going to graph is 2 pi over that value of b, which we know b in this case is 1/2. So it's 2 pi over 1/2, or in other words, 4 pi. That's the period of that trig function. And then we worry about a step size. Now, if you never learned it this way, I recommend that you do actually watch my videos on graphing trigonometric functions, because it is a better way to graph trig functions, is to worry about the amplitude, the period, and then the step size. That basically dices up your period of your function. Remember, we're dealing with a sine curve here. You're dicing that up into 1, 2, 3, 4, well, technically 5, right? 1, 2, 3, 4 sections, but into 5 edges. So, but you have 4 subsections. So I'm going to take that whole entire period and divide it by 4. The reason why is because each of those little subsections gives you a very important key point on that graph. So let's see, period is 4 pi. Divide that by 4 and we get pi. So that's the step size that we're dealing with in this case here. Now let's talk about the horizontal shift. That's the C part, sort of. It's not exactly C. And in fact, you can see that once you have factored out 1/2, you truly do see the horizontal shift. The horizontal shift is not apparent until you factor off the lead coefficient of x. And a lot of students remember this as negative c over b. So I'm going to write it that way, but in reality, it's just the shift so many units left or right after you have done the factoring. But I'm going to go ahead and say phase shift, and this is negative c over b. And if you were to look at the original problem, the opposite of c is pi over 6. Divide that by 1/2, and it's 2 pi over 6, or in other words, pi over 3. If you take a look at our factored form, you will see that pi over 3 is exactly what would turn that argument into 0. So that is another way you could have done it, but it is pi over 3. And now I will go ahead, and now that I know my phase shift, I like to personally get this step size in terms of the phase shift, basically to have the same denominator. So that step size is 3 pi over 3. I just do that because it's going to make the mathematics a lot faster. Not better, but just faster. And finally, we have a vertical shift. That's what D is. So vertical shift, in this case, is just 1. It's up 1. So now that I've done all that, I then invoke kind of the idea of graphing trig functions, I'll graph the base function, which again is the reciprocal of the cosecant. That's going to be the sine. So let's go ahead and start with that. If you've watched my videos in the past on graphing trig functions, or if you were one of my students in a previous course, you know that I always start with the midline, which is basically the vertical shift. I do that because it just makes the graphing a lot easier. I'll go ahead and label that. Remember, the vertical shift is 1. So I'll say that this line that is dashed out here is at a height of y equals 1. Then I'll take a look at my actual function, which is the cosecant. Notice it's a positive cosecant, and so therefore I'm going to graph the positive sine. Let me go ahead and carefully graph the positive sine here. Now, before I begin, I just want to point out something here. Notice that I plotted 5 points because there are technically 5 key points when you're graphing a sine or a cosine or a secant or a cosecant. And so it's just good to kind of get those written down first. Well, that's a pretty decent graph of a sine function. It's only one period of the sine function, but a pretty decent graph of it. Now let's go ahead and see where that sine function should have started to be graphed. Well, the phase shift tells us where our first key point occurs. It's at x equals pi over 3. So I'm going to go ahead and label that here. Once I have the first key point labeled, I will get to the next key point, this guy in the middle here in brown. I'll get to that one by just moving by a step size of 3 pi over 3. So I started at 1 pi over 3 on my graph, and I'm going to add 3 pi over 3 to land at 4 pi over 3. I'll add another step of size 3 pi over 3 to land at 7 pi over 3. Add another step of size 3 pi over 3 to land at 10 pi over 3. And finally, a last step size 3 pi over 3 to land at 13 pi over 3. And this is a beautiful kind of setup of our problem. The next thing that I tend to do is find out where the y-axis is. Now that we've figured out all the x values for our plot here, I'll just graph the y-axis. It's only a little bit off to the left-hand side. I'm trying to find my ruler here. Let me get my ruler set up. So let's see, it's about maybe this far over. I'll go ahead and graph a y-axis. Once I've done that, I happen to know the height of the midline is 1. Let me go ahead and erase this off to the left here. I'll just say this is a height of 1. And we know that the amplitude of our trig function is 2. So that means the distance between this midline and the apex, or the highest point, is a distance of 2. So 1 plus 2, or 3. And the distance from the midline down to the bottom, or the minimum for this graph, is going to be a distance of 2. 1 minus 2 is a -1. Halfway in between 1 and -1 is the x-axis. So let's go ahead and plot that in there very conveniently. And there you go. I'm going to actually label that x-axis right over here. And this is the graph of the sine function. We don't want the sine function. We actually want the cosecant. So let's go ahead and graph the cosecant function. That involves just putting a vertical asymptote wherever our sine function crosses its midline. Once we're done with that, you can see this beautiful kind of setup for our actual curve, which is the cosecant curve, and I'll draw that in, let's draw that in blue. And as we should know already, it connects to the maximums and minimums of the sinusoidal curve and tends to positive and negative infinity as it approaches the vertical asymptotes. So let's go ahead and do that. Now, I want to be very clear, this is only one period of the cosecant curve. So this is kind of something you need to be aware of. It's not the entire cosecant curve, but it's one period of the cosecant curve. I tell my students you are perfectly okay to leave that brown sinusoidal curve in there for reference, but for this problem, I'm just going to erase it. There's no need to really keep it in there. So there we have it. In blue is the cosecant curve. Now we're asked to connect a couple points together that exist on this curve. One point is at, let's see, 2 pi over 3, comma, f of 2 pi over 3. Well, 2 pi over 3 is roughly, and I'll do this in red, 2 pi over 3 is roughly around here, comma, f of 2 pi over 3. So I'll just write that in here, 2 pi over 3. Oops, that was supposed to be a pi there. All right, so that's our first point. And then the second point is supposed to be at pi, comma, f at pi. Well, pi, where does that occur? That's at 3 pi over 3, which is actually not too far away from this point. It's kind of a boring problem like that. Sorry about that. But this is the point pi, comma, f at pi. And our goal is to find the equation of the tangent line or the secant line connecting those 2 points. So graph the function and the secant line to the function going through the points 2 pi over 3, comma, f of 2 pi over 3, and pi, comma, f of pi. Bringing up the handy dandy ruler for this project, I'll again graph this as I have been with my other ones. I'll just graph this in red. Why not, right? So this is the secant line connecting those 2 dots. Not a very fun problem other than just drawing and connecting the dots, but now we're asked to find the equation of that secant line. Something you should be very aware of is this idea of finding equations of lines is actually pretty prominent in calculus. It's not something that you think would be prominent in calculus, but it is. It happens quite often. When you're asked to find the equation of a line, whether it's called a line or whether it's called a secant line or whether it's called a tangent line, all of those just say line. And when you want the equation of a line, you need 2 things, a slope and a point. All lines have a slope, and all lines contain a point. Technically, vertical lines do not have slopes because their slopes are undefined, but this is not going to be a vertical line, so let's not have that discussion. All right, let's find the slope at least. That is just the difference in the y values divided by the difference in the x values. So this is going to be the difference in the y values divided by the difference in the x values. You can easily see you're going to be required to evaluate trig functions quite often in calculus. If you have not had trig, drop calculus right now. You need to take a trig course. There's just no way around it. You will end up causing more failure for yourself if you suck at trig. All right, let's go ahead and do this. So plugging in to f here, pi. Well, f at pi is just going to be 2 cosecant of pi over 2 minus pi over 6. Sorry, my pen on my digitizer tends to go wacky sometimes. Let's see, pi over 2 is 3 pi over 6 minus pi over 6. 3 pi over 6 minus pi over 6 is 2 pi over 6 or pi over 3. So that's 2 cosecant of pi over 3. Now I want to be incredibly forthright with you as you go through your calculus course, whether it's in my class or somebody else's class. It is assumed that you know how to evaluate the cosecant of pi over 3. You could easily just draw out a right triangle that has, even though this doesn't look like it, has a pi over 6, a pi over 3 angle, even though, like I said, this looks more like a 45, 45, 90, but whatever, right? And now we know cosecant is hypotenuse over opposite. And so we want the hypotenuse over opposite when it comes to the angle pi over 3. Hypotenuse being 2, opposite being root 3. So this is 2 over root 3. Now I have to admit, that's not the best number in the world, but that's just how life works sometimes. Now we need to figure out what f is at 2 pi over 3. It's the same cosecant function, so if you plugged in 2 pi over 3 in for x there, you get 2 pi over 3 times 1/2, or pi over 3 minus pi over 6. And that's 2 pi over 6 minus pi over 6, or a pi over 6. Again, referring to our right triangle here, we know that the cosecant is hypotenuse over opposite. Almost said adjacent, but it's opposite. And so that would be 2 over 1, which gives us 4 plus 1, or in other words, 5. Now we just go back and plug those things into our slope formula. And as gnarly as that looks, we can totally clean that up. It's pretty okay. Multiplying numerator and denominator by 3 root 3, we get the following. And of course, this can be cleaned up a little bit, so I'll go ahead and do that cleanup here. Now, oddly enough, I tend to not be a fan of rationalizing denominators. However, in this specific case, it might be helpful to rationalize this denominator. So if you imagine multiplying both numerator and denominator by the square root of 3, not that it's a necessity, but I'm just going to do it here. Multiply top and bottom by the square root of 3, and let's see what we get. You can see that that actually does help out because each of those terms in the numerator are divisible by 3, and so our final answer for the slope is going to be the following. Now that is not a beautiful slope, and I did all that work, and I really want to move that over because it's a bit of a mess here, so forgive me while I just grab this and slide this onto the left-hand side here so it's away from my graph. In fact, I'll do it a little bit more. Now that we have the slope, we can go ahead and also state the point. There's actually 2 points on this curve, but probably the easier of the 2 points is the one at x equals 2 pi over 3, comma 5. So I'm going to go ahead and use the 2 pi over 3, comma 5 as the point. Great. Now we have a slope and a point. I can find the equation of that secant line. The equation of any given line, as long as you're given a slope and a point, is y minus y1 is equal to the slope times x minus x1. And let me zoom in so I don't mess up my handwriting. Slope times x minus x sub 1. All right, let's plug in all that information that we've discovered here. This implies that we have y minus 5 is equal to our slope, which is 4 root 3 minus 12 over pi times x minus the x value for our point, which is 2 pi over 3. And let me clean that up because it's pretty ugly. Some instructors will allow you to leave it in this form. However, if you're working in an online homework system, generally speaking, you have to have this in slope-intercept form. So let's go ahead and isolate y here and distribute things through. It gets real messy, but you can do it. You've had all this algebra in your background. You can totally do this. Get down to here and you'll probably want to combine those two constants as well. There we go. Now, if you're wondering how I got, because I have a feeling some people are going to say, wait, what just happened? How did you get a negative 39 there? I know that almost always will happen. Distribute. That's the easiest way I could say that, is to just remember this subtraction is affecting this term and that term. So that's technically not a negative 24 over 3. It's a positive 24 over 3. Plus 15 over 23, or plus 15 over 3 is going to be a, 39. So it will be a 39 thirds. Now, when you glue it back into that single statement, you don't want to say minus with a plus sign there because you want that to be a positive between the 8 root 3 and the 39 in the long run. So anyhow, that's just a little bit of your old school algebra working in the background. This is called exact form. And I like exact form because I don't need to grab a calculator. I don't need to use technology at all to do a problem like this. Now, why don't we go ahead and just use Desmos to check whether or not our graph and our secant line in our equation is correct. Now, what you're looking at here is a graph of the cosecant curve that we just figured out, and I restricted the domain of this curve to be between pi over 3 and 13 pi over 3 because that's the way we drew that originally. If you don't know how to do that in Desmos, it's pretty easy. You actually start with just your base function. So let's pretend as though I didn't have this domain restriction and you had just written out 2 cosecant of 1/2 x minus pi over 6 all plus 1. If you want to do a domain restriction, at the beginning of your function here, you would start with a curly bracket brace there. And then before writing your function, you put a colon, and then in between the colon and the curly bracket brace, you would start your domain statement, which is that you want all x values to be between pi over 3 and 13 pi over 3. So I'll type pi for pi over 3, and I want that to be less than or equal to x, and I want that to be less than or equal to 13 pi over 3. And that's how I get my domain restriction. If you don't like this reverse contrast, by the way, on the screen that you see here, you can always go in and turn that off. Wow, that's super bright now. But there you have it. It's just kind of nice to have reverse contrast every once in a while. The other stuff that I have in there, I just graphed the asymptotes, the vertical asymptotes, pi over 3, 7 pi over 3, and 13 pi over 3. I also plotted the 2 points that we have interest in our secant line going through. So that's 2 pi over 3 comma 5, and that's pi comma f of pi. And let's go ahead and just compress that. Now, here's the secant line we just computed. To verify that that's actually the secant line, I'm going to turn that on. There you go. You can easily see that is the secant line. And if you like the reverse contrast better, again, you can still easily see that's the secant line. Very, very nice. Now we're going to change it up a little bit. Let's suppose that we have the same example that we just played with there, but this time we're asked to find an expression for the slope of the secant line going through the points 2 pi over 3 comma f of 2 pi over 3 and some arbitrary point on that curve placed at x comma f of x. So if I hop back just to showcase what I'm talking about, I'm really stating that rather than having, oops, I didn't mean to erase all that, but rather than having a secant line connecting 2 pi over 3 to comma f of 2 pi over 3 to pi comma f of pi, let's suppose that we instead have a line connecting that 2 pi over 3 comma f of 2 pi over 3 to any other arbitrary point on the curve. It actually doesn't even need to be on this branch. It could be on the branch way down here. And so this, let me go ahead and write it in red and zoom into it as well. This point right here, that point could be x comma f of x. All we need to know is what is the slope of the line connecting 2 pi over 3 comma f of 2 pi over 3 to that point x comma f of x. In other words, what's the slope of this secant line? And that's the idea that you're going to head to in calculus, at least for the rest of this course. So that's the entire idea of what we're doing here. Let's go ahead and find the equation for the slope, or the expression for the slope, really. We know that the slope is just the difference in the y values, so y2 minus y1, over the difference in their corresponding x values, x2 minus x1. Well, the y values that you see in these points are going to be f of 2 pi over 3 minus f of x, and the corresponding x values are 2 pi over 3 and x. So we go ahead and insert all that stuff into our function. Our function, evaluated 2 pi over 3, we know from our previous example, is 5. Minus the function itself. So minus, I'm going to put this as a quantity. The quantity of 2 times the cosecant of 1/2 x minus a pi over 6. And then plus 1. And that plus 1 is the reason why I put this second set of brackets on there, because you have to distribute that negative through in the numerator. In the denominator, we just have a simple 2 pi over 3 minus x. The next thing I'm going to do is distribute that negative through and combine like terms. That can be done in one step since you're in calculus. And finally, I'm going to go ahead and multiply numerator and denominator by that 3 because I dislike compound fractions. Most people will dislike compound fractions, so get used to cleaning up compound fractions like this. Multiplying both top and bottom by 3, we get the following. And there you have it. That is an expression for the slope of the secant line going through 2 pi over 3 comma f of 2 pi over 3 and the point x comma f of x. And I was just about to leap away from this problem, but let's actually go ahead and go to Desmos and play with this a little bit. So here we are back at our original Desmos applet that we were playing with a few minutes ago. And now we want to adjust this so that our secant line is not going through 2 pi over 3 comma f of 2 pi over 3 and pi comma f of pi, but instead it's going through 2 pi over 3 comma f of 2 pi over 3 and some arbitrary point a comma f of a. We were writing it down as x comma f of x, but actually I'd like to mark it as a comma f of a. So here's how I'm going to do this, and here's how you would do this as well. Notice that the point we're plotting right here is 2 pi over 3, I'll just zoom into it, it's 2 pi over 3 comma f of 2 pi over 3. What I'd like to do for the second point is not have it at pi comma f of pi, but instead have it at a random number a comma f at a. Now, I know that we were supposed to be looking at x comma f of x, but Desmos cannot parse that. If I were to write in x comma f at x, Desmos does not know what to do. You can kind of see it over here if you zoom in, that it just doesn't know what's going on here. So you need to give it what we call a parameter. And so I'll use a as my parameter, a comma f at a. Or if you want to use b, actually I think b might be a little bit easier because I call a my anchor point. So let's let b be the value. Now, all you need to do is click that add a slider button, and then I'll change the values of b to be any number I want between pi over 3 and 13 pi over 3. So I'll type in pi over 3 as the lowest number for b, and 13 pi over 3 will be the highest number. Now I'm artificially saying that that's what I want my x values to go between. You don't actually have to just limit it to those, but I'm deciding to do that here. And the step size, I'll just do it as 1/100th. Now, if I move this, you can see there is a point on the curve that is some b value. In this case, b is 4.197 and f at b is 3. And then as I move it, obviously it changes. And actually, if I keep moving it, you see it goes to the lower branch, right? So you can see it can hop over to that lower branch. So for now, I'm going to keep it in the upper branch so that we can talk about this. Now I want to create a secant line between the point that we were given, 2 pi over 3 comma f of 2 pi over 3, and this new point. Now, if I were to just write down, let me turn off my old secant line. Okay, so I'm going to turn that off. In fact, I should just delete it to get it out of our eyesight. We happen to know that all equations of lines are of the form y minus y sub 1 is equal to m, oops, that was supposed to be an m, times x minus x sub 1. The problem here is that we need to replace x sub 1 and y sub 1 with a and f of a. So I'm going to replace x sub 1 with a and y sub 1 with f at a. Now, if you notice, it says add a slider for a. Oh, that's because we were using b. Actually, sorry about that. We used b as our value. Now, notice what's going on here. There's this weird kind of curve going in here, and that's because I'd already defined what the slope was. I'm going to remove this definition of the slope in a moment, but I just want you to note that the slope you cannot write as m is equal to all this stuff. The reality is that this value of x is not x. Remember, it's b. And this value of x is, again, not x, it is b. When you make that change there, our equation for our line is y minus y1 is equal to slope times x minus x1, where in our definition here, our x sub 1 and y sub 1 are b comma f of b. So wherever I would normally write an x sub 1, I'll replace it with a b. And wherever I would normally write a y sub 1, I'll replace it with f of b. Now that's, as long as that's clear to you, then we have to worry about the slope. And there's two ways you could have written this. You could have actually written the formula for the slope in there, but I decided to write the slope as its own formula above and then just write m there. The formula for the slope we had just computed is -6 cosecant of 1/2 x minus pi over 6 plus 12 over 2 pi minus 3x. But remember, the x value for this point right here is what we are calling b. And now what you can do is you can change b and the secant line will change accordingly, which is kind of nice. Also, what's really nice about Desmos is I can just grab that and move this. That's super nice. Now notice our anchor is at 2 pi over 3 comma f of 2 pi over 3, and our point b is currently at 5.667 comma f at 5.667. And as you move that b comma f of b closer to our anchor point, something magical happens. It ends up approximating what we would call the tangent line to the curve. So really, the ultimate goal in calculus is to bring these 2 points, at least in calculus 1, I should say, is to bring these 2 points infinitesimally close together. You don't want them to actually be the same point because you'll have some issues. If they are the exact same point, you would then get division by 0. And we'll talk about that in the next video. But for right now, you can see it's kind of beautiful that you can drag that point as close as you want to the anchor point at 2 pi over 3 comma f of 2 pi over 3. And you get this approximation for what the actual tangent line is, not secant, but tangent line for our curve at 2 pi over 3. And again, just to let you know, you could technically allow b to be large enough so that it's on the other branch. It's totally fine. You could have a secant line connecting 2 points between 2 completely different branches. That's totally okay. It's just weird, but it's totally okay. Now that we're done with that, let's go ahead and go into the last little topic in this video, which is the average rate of change. You have learned this in your intermediate algebra class, your college algebra class, and your pre-calculus course. It's just the slope of a line containing 2 points. That's really the average rate of change. The definition states the average rate of change of a function between 2 points, a comma f of a and b comma f of b, is just f of b minus f of a divided by b minus a. That is, the average rate of change is the slope of the secant line. So if somebody asks you to find the average rate of change of a function between 2 given points, really they're just asking what's the slope of the line connecting those 2 points. It's a fancy way of saying what's the slope of the secant line connecting these 2 points. But it's actually easier to say what's the average rate of change. It's just faster. So let's go ahead and go back to Desmos and build a table of values to investigate the average rate of change for the function from our previous examples as x gets really close to 2 pi over 3. So here we are back in Desmos, and the problem actually asks us to build a table, but I'm just going to showcase one way you can do this sort of without a table. Since we already have the slope function written here as a function of this point b comma f of b, I could drag that point closer and closer. As that point gets closer to 2 pi over 3, we do actually see the average rate of change, which is again the slope of the secant line, adjust accordingly. And so as we get closer and closer, we see the average rate of change is roughly negative 3.32, and then a little bit closer it's negative 3.4543, and so on and so forth. But it's very hard to fine tune this because we're adjusting using a mouse here. So another way you could do this is by building a table in Desmos. So you can go to the add item button and just click on table. And let's see how this is done. In this case, I am going to use X's and Y's sort of. I'm going to go ahead and just say that we're looking at 2 pi over 3, and we want to look at this slope as x gets really close to 2 pi over 3. So I don't want to look at 2 pi over 3. I want to look at 2 pi over 3 plus or minus a small little wiggle. So let's say plus 0.1. All right. And now let's find out what the slope of this secant line is at 2 pi over 3 plus 0.1. I decided to drag the table down because I want to showcase this using a function m. It would make my life much easier. So I'm going to create a brand new function, capital M, because I'm using little m for something. I'll say capital M of x is equal to, and then we'll say it's a fraction where the numerator is a negative 6 cosecant of. So you notice I'm typing in here our result of computing the function, or the slope. So cosecant of 1/2 x, and then minus pi over 6. And let's see, we had a plus 12 there. And in the denominator, we had a 2 pi minus 3x. There we go. And notice it starts graphing stuff. You could just turn off that graph. That's annoying that it's there. Now what I'm going to do for this y value is, rather than having to type in m at capital M, that is, at 2 pi over 3 plus 0.1 and so on and so forth, I'm going to change the definition of the output to be capital M evaluated at this x sub 1. Notice it automatically fills that in for me. And now I can just go to the next part of the table and look at 2 pi over 3 and make that point a little closer. So instead of 1/10 of a unit away, let's do 1/100th of a unit away. And if you want to get even closer, you can look at 2 pi over 3 plus 1/1000th of a unit away. And you can even get more finely tuned here by looking at 2 pi over 3 plus 0.0001 or 1/10,000th of a unit away. So you can see you get much finer detail if you build a table here. You could also check it on the other side. That is, we're only looking at 2 pi over 3 plus a positive wiggle. So we're looking at stuff over here, the slopes or the average rates of change for our function when our change is positive. But what if our change was negative? What if our non-anchor point was behind or to the left of our anchor point? Well, you could still build a table for that. In fact, use the same exact table. It's 2 pi over 3 minus 0.1, and then 2 pi over 3 minus 0.01, and 2 pi over 3. You get the idea, right? So you could do this all day long if you really wanted to. But you could see that on either side of the anchor point 2 pi over 3 comma f of 2 pi over 3, you are approaching, or I shouldn't say you are, I should say your average rate of change is approaching negative 3.4637516 or something like that, right? Negative 3.46 roughly. You can even throw some more zeros on there just to see, right? So if I threw a bunch of zeros on these, you see that it starts anchoring down. You do have to understand that Desmos does break. You can easily break Desmos by throwing too many zeros in there. So that's just a heads up. I would only trust it out to maybe 3 decimal places. So negative 3.464. This is a great example of the fact that Desmos is still based on computer technology, and there are some very famous examples where you can easily break it.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.